All right, so what we want to talk about now is how does the molecular structure, so what does the molecule actually look like, and how does that relate to acidity, and then conversely basicity? The overarching theme of how acidic a molecule is once that acid, right, that molecule has given up that proton, right? Acids are proton donors, so they're going to give up a proton. So once it's given up a proton, how stable is the anion that's resulted from it, right? So how stable is that molecule once it's given up a proton, right? The biggest idea behind this is the more stable that anion is, the greater the acidity, right? So the molecule is going to be much, much more acidic if it creates a stable conjugate base, right? So that anion that's formed, if it's stable, then it's going to be a stronger acid. So the question is, what makes it more stable? So let's kind of go through these. So here on the left, I'm going to go through some of the factors, and then I'll give you kind of a cheat, a way to kind of look at if you're approaching these. So how stable an anion is comes from several things. The more electronegative, right? So if you remember, we can take our periodic table, and so let me just put it over here. So if we have our periodic table, it looks something like this. And remember, fluorine is the most electronegative. And so as we work our way towards fluorine, we get more electronegative. All right. The other thing we have is the size. All right. So the more electronegative, the better in terms of acidity. Also, the bigger the atom is, all right, the better it is at acidity. So if you remember, larger atoms are at the bottom. Right, so what we're going to tend to think is that if you're going to the right, right, so if you're going carbon, oxygen, nitrogen, so if we kind of do it over here, carbon, nitrogen, oxygen, fluorine, we're going to get more acidic as we go to the right. And that's because we're more electronegative. As you go down the periodic table, you also get more acidic. So if we're looking over here and we go fluorine, chlorine, bromine, iodine, we get more acidic as we go down the periodic table, right? So we get those two ideas. So the more electronegative you are, the better you are at stabling that negative charge, right? Electronegativity means you like electrons, so that kind of makes sense. The larger atom comes from the idea that you have all this electron cloud density, and if you have a whole bunch of electrons anyway, adding one extra one doesn't make a huge deal. All right, the next one, and we're going to go back and talk about each of these in detail and look at some examples. Resonance is when you can move electrons around. So I think the one we've seen the most, and I'm going to put it right here at the top middle, is our carboxylic acid. And so once it's given up that proton, so this is a carboxylic acid that's lost that hydrogen. If you remember, resonance is where we can move these electrons here and up. Right? And we can move that negative charge around. And so the more places you can spread out that negative charge, the better, right? You're delocalizing that negative charge. So that's where that term delocalization comes from. You're going to delocalize that negative charge. And I think when we're talking about resonance, one of the examples we did is if you're carrying some furniture or couch, if you're moving in your dorm or something like that, the more people helping you carry it, the lighter it is. Same thing with the negative charge. The more atoms carrying it, the better. Inductive effect is when you have electronegative atoms near a negative charge, right? So you're not physically moving it, but if you have electronegative atoms near it, it's going to help start pulling that cloud away, right? So resonance is much stronger, but inductive helps. And then the last one is our orbitals. And the more S character, the more acidic you are. And so if you remember S character, if we talk about orbitals, our three that we've done, spent some time with is sp3, sp2, and sp. So you remember this with the hybridization? And so the more S character you have, the more acidic, meaning that if you have a carbon atom or some atom that's sp, it's going to be more acidic than the same atom that's in sp2 or sp3. All right, so you might be asking, well, which of these is more important, or where do I start? This is where this little like cheat kind of helps. So if you look at this caro, some people call it cardio, they add a D for the delocalized induction, but it's kind of up to you. Let's just start. So the first one talks about the charge. Right? And so we're talking about the charge of a molecule. Where that comes from is, let's compare two molecules. So if we have water, so H2O versus hydronium, H3O plus. Right? So if a molecule is charged, it's already picked up that extra proton. Then if this molecule gives up a proton, so this is me showing it, it's going to lose that proton, right? Because it's going to give up a hydrogen. It creates a sodium hydroxide, or just hydroxide. There's no sodium. And typically we'd have a metal, but it just becomes hydroxide for this example. So it gave up that proton. If this one does the same, right, then it's going to give you water. And we talked about an anion being very stable. Well, this one doesn't even have an anion, right? It's just water, right? And we know that water is extremely stable. So that's why typically if a molecule has an extra proton already, then it's going to be the most acidic, right? So that's where this idea of charge comes from. All right, the next one is atom or atoms. So what you want to look at is the actual atom. So it's going to be these two combined. All right, so I'm just going to put an A for atoms. So you actually want to look at the atom. So a question that I could give you, and if you don't mind, I'm actually going to erase some of this just to try to clear out some space. If I give you a molecule, and so we had CH4, so methane versus NH3, and ask you, okay, which of those two is more acidic? We're going down our chart. Neither of them has a charge. So we move next one to the atom. So we want to see the atom that's holding the hydrogen. In this case, it's a carbon, and in this case, it's a nitrogen. And so we look for them on the periodic table, and it says they're on that same row. And so whichever one is more electronegative is more acidic. So then my answer would be ammonia. Okay? Doesn't matter how many hydrogens, it just matters which one's the most acidic. So which one's going to pop off first. So the second thing you should look at is which atom is it on. Now, the next one is if they're the same atom, right? So let's say, for example, you have an alcohol, H3OH, so methanol versus acetic acid. All right, so this is the example we just did above. So right here with the resonance, we're going to look at atom. Right, so there's a carbon with hydrogen, there'd be a carbon with 3 implied hydrogens, but we know that if we go across, oxygen is more acidic. So we only care about the oxygen atom. They both have a hydrogen, so the atom one doesn't help, right? They don't have a charge, so that didn't help. So we're in resonance. The oxygen here can't draw resonance, right? There's nowhere to push those electrons. The bottom one can, right? So we can do the resonance structures we just saw here in purple. And so that's why this one would be more acidic. Okay. Induction would be adding some fluorine. So if we compared, so let me erase these down here at the very bottom, and I know the page is kind of getting a little busy. But if we have something like this, where we have CH3OH, or we have CF3OH, we've gone through charge, no charge, atom, they're all the same atoms, right? Because the oxygen is holding the hydrogen, right? It's the oxygen holding the hydrogen. Neither of them can do resonance. So now induction tells me if you put something electronegative near the atom that's donating that proton, right? Near that acidic atom, it's going to make us more acidic. So fluorines are really electronegative. So they're going to pull that electron density. And so this one would be more acidic. Right? And we're going to go through each of these in more detail. I just kind of want to give you that quick overview so you can come back to this. Last one, it says O for orbital. And the orbital that we're actually going to care the most about is that S character. All right. And so we said if we compare the groups, right, if you're sp, you're going to be the most acidic, then sp2, and then sp3. All right. So what I would keep in mind is if you kind of remember this chart, right? And as you're kind of going through it, just remember C stands for the charge, A is for the atom, this is for resonance, induction, orbital. All right. And so that's going to be kind of your sequence. So start at the front and work your way through. And if they don't make great sense yet, we're going to actually talk about each one in a little bit more detail right now. So that first one is that electronegativity. And so essentially, the more electronegative, the more you're willing to have a negative charge. All right. So here's your groups. And so here's our carbon, nitrogen, oxygen. And so we think about electronegativity, it goes carbon, nitrogen, oxygen, fluorine, right? And we get more electronegative as we go towards fluorine. So what we would expect is that this hydrogen that we're giving up becomes more acidic as we get more electronegative. And that's what we see here. The other thing, remember pKa, we talked about this before. It's a measure of how acidic that molecule is, right? So it's actually the dissociation constant for that hydrogen. But a good way to think about it is it measures how acidic something is. The smaller this number is, the more acidic. So 50 is a pretty big number. 38 is a little bit smaller. 16 is even smaller. So we get more and more acidic. Conversely, if you look at the conjugate base, it's going to go in the opposite direction. So it was easier to rip off this hydrogen. So it's the weakest base of these. It's really, really hard to pull off this hydrogen. So if you do end up taking it off, it's going to be your strongest base because it wants to put that hydrogen back. The other one is size, right? We said as you go down the periodic table, the atoms get bigger, and so they're better adapted at accommodating that extra charge, right? So within the periodic table, the larger the atom, the more likely it is, or the better it is at accommodating that negative charge, right? And the notes say bearing that charge so it can hold that charge, right? So if we look at sulfur and oxygen, they sit right on top of each other. So actually do that backwards. Oxygen's on top and then sulfur. And so remember, as we go down the periodic table, we're going to get more acidic. And so we actually see that here, that sulfur has a pK of 7, right? Methanol has a pK of 16. So that trend just keeps holding true, right? As we go down the periodic table, you get more acidic. And it's just because you go down the periodic table, we're adding more shells, right? So there's more electrons in that molecule. What I would take home from these two is this periodic table trend. So as you go right and down the periodic table, you're going to get more acidic. Right? So if we're thinking about our cheat sheet, right, of how do we tell if a molecule is more acidic, remember charge is our first thing, and then the atoms is the second, right? So if they don't have a charge on them, then the next thing we want to look at is the atom, right? So where in that molecule is that acidic proton coming from? I find the atom, and then I compare them on the periodic table. And so, for example, if I'm comparing carbon to fluorine, then that fluorine is going to be more acidic. Right? If I'm creating, and let me just actually, oxygen, phosphorus, sulfur. If I have something like NH3 versus SH2, remember, it doesn't matter the number of hydrogens. It just matters where they are. So if I compare nitrogen to sulfur, right, those are the two that we're asking for in the question. So if I ask you to compare these two, sulfur is a little bit farther to the right and down, so it should be more acidic. So this would be my acidic one, right? And so remember, it's just going to be that same trend, chlorine, bromine, iodine. So iodine would be the most acidic of all these molecules, right? And we would think carbon would be the least, right? And so it's that same trend. As we kind of move to the right and down on the periodic table, we're going to get more acidic, right? So as we're building through this chart, right? Carbon is the charge, or sorry, not C is for the charge, A is for the atom. All right, so based on what we just talked about, pause the video and rank the top 3 as most acidic to least, rank the bottom set as most acidic to least. All right, go ahead and give it a try, and then we'll do it together. All right, so as we're looking at this, remember, we're going to draw our periodic table. And as we go right and down, we get more acidic. And so if we're looking at this, these are all carbons here in the zigzag form, and then a nitrogen. So the nitrogen is the farthest to the right. And so if we go through this, let me just do a cheat sheet over here for right carbon, nitrogen, oxygen, fluorine. And we're getting more acidic as we go this way. So nitrogen is going to be the acidic one. So let me highlight that. Same thing with oxygen. And then these are all carbons. So as we go through carbons, the least acidic, then nitrogen, then oxygen. So here's my oxygen. And so we get something like that. One thing I want to point out, if you have a molecule like this, so if we compare the two in red, just be careful that even though I just told you the oxygen is the more acidic, there's actually a hydrogen on that oxygen, right? There's a hydrogen on that nitrogen. If you're looking here, well, this one has an oxygen, there's not actually a hydrogen on it, right? Same thing here, there is a hydrogen on the nitrogen. So what I would actually be comparing is the only places that have hydrogens is on the carbons. So now when I'm comparing them, I'm comparing the carbon hydrogen versus the nitrogen and the hydrogen. So in that case, if we're comparing these two, this one wins. All right, so there has to be a hydrogen for you to compare it. Same thing for the bottom one. If we're looking at our periodic table, it goes fluorine, chlorine, bromine, iodine. And remember, we also get more acidic as we go down the periodic table. So if we rank these, this would be the most acidic, second, third, fourth. All right, to make sure you can do this, I think one of the things that's very common question to see is give you a set of molecules and ask you which one's the most acidic. And so just remember, it doesn't matter how many hydrogens you have, it's just which one is going to most readily give up that first proton. All right, the next one, right, if we're kind of moving along our chart, we said that we have charge, atom, and then the next one we get to is resonance. Okay? So resonance is just going to talk about that delocalization of electrons. And if we kind of skip down to the bottom, here's our resonance structures, right? It's given up that proton. Right? This is the hydrogen we want to give up. Same thing for the alcohol. And so the ones highlighted in green are those protons we're actually going to kick out. If you're looking at this resonance structure, you can push your electrons in and up and move the negative charge, right? So resonance is when we can move those electrons and move those resonance charges around the molecule, right? So it's here and now it's here. If we skip back up to the alcohol, it's stuck on one atom, right? And we can't move it around. The more we can move that negative charge around, the more stable that anion, so more acidic. And so we actually see that this is the more acidic molecule. All right. So if we're comparing those two, the one that has that resonance is going to be more acidic, right? And the more places you can move it, the more acidic it's going to be. Induction. Here's a similar example to which we talked about. So one thing that's already highlighted is the hydrogen that's most acidic is here in red, right? So we're giving up this hydrogen that's on the oxygens, right? You might be asking, well, fluorine you said is more acidic than oxygen. Yes, but there's no hydrogen on these fluorines, right? So it's got to have a hydrogen to give it up. But how the fluorine does help is if we have these groups, right, they're the exact same thing, except for the fluorines and the hydrogens have switched. These are electron withdrawing, right? So if they're electron withdrawing, they're going to pull my electron density away from that proton, right? And it's going to make it easier to give it up, right? So it can pop off that proton. Okay? A couple things. The more fluorines there are, the better. So if we had one of these molecules that only had one fluorine, then it probably wouldn't be as good as the trifluorine, right? So adding each one, so 1 would be okay, 2 would be better, 3 would be the best. The other thing that happens is the closer it is to it, the more it helps, right? So if you have your fluorines here, it's pretty close to that proton that we're giving up, and it makes a difference. if you notice, we're inserting an extra CH2 in between the two. And so the further away it gets from that acidic proton, the less and less it helps, right? You can see that as we keep moving these fluorine groups back, and let me just highlight them. And so we're moving them further away from that acidic alcohol, right? There's more carbons in between, and it helps less and less. So the smaller the pK, the more acidic. So you can see this one was the most acidic molecule. The fluorines were the closest. We get them a little bit further away. It becomes less acidic. We move them even further away, and it becomes even less acidic. All right, so the closer those electron withdrawing groups are, the more they help. All right, so let's try one. So here's an example of that. So look at this problem and rank these from most acidic to least. And I'll pause the video and give it a try. All right, how'd it go for everyone? So I think the first thing is our chlorines are electronegative groups. They're not as electron withdrawing as fluorine, but they're still pretty good. And so first thing I would say is this one doesn't have any groups. So this is probably the least acidic, right? So if we're ranking these, this would be 4, right? With 1 being the most acidic. Now, these are the same groups, right? Chlorine, chlorine, chlorine. So the one that's closest is probably the best. So 1, 2, 3. All right. So our acidic proton is going to be this one. And so the closer that electron withdrawing group is, or that, the electron withdrawing group to that acidic proton, the more acidic it is. All right, the last thing, let's compare these two molecules. All right, so if we're looking at these, right, we have our carboxylic acid, and we have our carboxylic acid. And the only difference is this one's a chlorine, this one's a fluorine, right? They're the same distance. Then the more electronegative atom is more acidic. So then if we're comparing these two, then that would be my more acidic one. All right, let's try one more set. So again, rank these from most acidic to least. Go ahead and pause the video and then we'll do it together. All right, so how did everyone do? So I think this one has a couple things. So let's kind of write out our structure. So we want to do charge, atom, resonance, induction, and then our orbitals. So what I would go through is none of these have a charge. Right, so next we move to our atom. It looks like for all of them, the most acidic proton is on these OHs. Right, so we found that group. So I think that one's good. Now the next one is resonance. Right, so resonance means it can move around. If you have that double bond next to that acidic one, we're gonna have resonance. So let me just put a little R by the ones that can do resonance. Right, so it's probably those two. So which means those two are gonna be my most acidic. All right. The next thing is induction. Right? And so induction is when you're near an electronegative group. Right? So we know that the two with resonance are going to be the most acidic. And then this one also has induction. And I'll put another I by it. So we know that it has induction. So this should be 1 and then 2. All right, we come down to this one. And we're trying to decide which is the next acidic. All right, neither of them have resonance, but this one also has induction. So this becomes 3, 4. All right, and so just remember that resonance is more important than induction. So we're kind of going down this kind of chart. Okay. All right, so hopefully that was helpful. Last group is our orbitals, right? So we're going to look at our hybridization. And so if you remember S character, we could look at the atom and name it sp3, sp2, sp. And so the greater the S character, the more acidic, right? And if you remember, it's because those S orbitals are actually a little bit lower in energy. And so that's what accounts for this pK difference, right? So one thing I do want to highlight is, while this helps, it's not as good as the atom. right? So water has a pK of 15. Even though alkynes, right, which have that triple bond, which is going to be that sp, right, is a pK of 25. So a significant difference. Okay? Here's our triple bond versus our double and our single bond. And so let me actually highlight those so we can come back to these other ones. But if we highlight these, you can see a big difference, right? So our alkyne is going to be sp, sp2, sp3. And the greater the S character, right? This one's 50%, this is a third, this is a quarter. So 50%, 33, 25. The more S character, the more acidic, right? And so that's exactly what we're seeing here. It does highlight that the atoms make a bigger difference, right? But we want to be careful about that S character. So the more S character, the more acidic. Last thing, we've talked about giving up protons, right? And that's the best way to think about acids. One thing we'll see a little bit as we go later on is we'll see Lewis acids, especially as catalysts. And so a Lewis acid just talks about Lewis dots, right? So if you think about Lewis dot structures, we put the dots around the atoms. So a Lewis acid is an ion that can accept electrons, right? And so it's something that can accept an electron pair. A Lewis base is anything that donates electrons, right? So the accepting and the donating have switched because we now, instead of talking about a proton, we're talking about an electron. Right? And so it's just something we'll come back to because we do use some Lewis acids and Lewis bases as catalysts and they help in some reactions. So, all right, I hope this was helpful.